So let's walk through an example of a multiple linear regression or ordinary least squares regression. So the difference, if you remember learning about correlations, whether it was this class or stats in high school or college somewhere, a correlation is the amount that one variable moves or changes when another variable moves and changes. So here we have people's age and income, and as they get older, their incomes typically go up. A correlation of 5,2 is represented here in this overlap. So think of these circles as the entire variance or variation in age and income. So the amount that they overlap is the amount that income changes as age changes. Same over here with education and work experience, and so less overlap means less correlation. Now, the problem with this is that these three correlations, let's say we have all three of these data points, age, experience, work experience, and education, we can't simply add them together and say, okay, we have now, that would be what, 1.42 correlation. That makes no sense. A correlation maxes out at 1%, or 1, sorry. In other words, 100%, meaning we're trying to predict income as well as possible, so we want as much overlap as possible. But the reason we can't add these three up is because they have intercorrelations themselves. So down here is our example. Age, work experience, and education are also highly correlated. All of them increase with time. And so together, we are still not overlapping the entire 100% of this variation in income, but it's more than any one of them alone. And so we move to a different measurement from R. We use R squared to represent the combined shared correlation of all these. Now, R squared in this case isn't a literal R squared as it was when we were just looking at a single indicator at a time. In fact, the formula, it's a little bit more complex, and we're not going to go into great detail, but it's this right here. R squared equals 1 minus sum of squared residuals over sum of squared total. So this is essentially the remaining error divided by the total variation, and 1 minus that gives us the part that's explained by our variables. So here's what we need to do. We need a way to measure exactly how much all three of these overlap with income at the same time so we can generate an R squared. Now notice that we're also interested in exactly how much age, work experience, and education independently affect income. So age, the portion that overlaps with income, is also overlapped by education and work experience to a great degree. So can we really say that the effect of age on income is this entire section right here? No, not if we're taking into account work, experience, and education. So what we have to do is we have to make sure these parts that are double shaded don't get double counted. This part that gets triple shaded is not triple counted. Does it matter which one we assign that variation to? Well, in the case of machine learning or prediction, it really doesn't. Any one of them can take it. And there's different ways of doing an MLR that will assign them to different variables. We're not going to worry about that. Let's just walk through an example of how to do this in Excel. And we'll do that before we get to Azure or other tools that are a little bit more advanced. We're going to use this insurance data set right here. Go ahead and download this. I've already got it up right here. What we have is 7 variables. And G, charges, is our label. That's what we're going to try and predict. So each row here is a customer. And the customer has 6 features that we've measured, and then an outcome, charges. And we want to see how much these 6 features predict or explain their level of charges. That's the role of an MLR. So before I get to that, let's first create a correlation matrix. So I'm going to go to data analysis. If you haven't already, you know the way you get this: file, options, add-ins. Make sure that here on Excel add-ins you have analysis tool pack checked if this is your first time doing this for this class. So we have this data. Once we do that, you get this data analysis button. Click on that. We're going to go to correlation. Input range is going to be all of these variables. I'm going to select that and then hold down Shift Control, go right, go down, and that takes us down here to a total of 1338 records. Labels are in the first row. Output range, click this first, then click this box and take this up here to I2. Let's print it out right there and just hit enter. Input range contains non-numeric data. First thing we learn is that a correlation can only run with numeric data. Now, hopefully you remember that from a prior chapter. So what we're going to have to do here is do some reformatting. I'm going to move region and charges over here. So I'm using Control-X, Control-C to cut and paste entire columns. I'm clicking up here to select the entire column at once. Move age over here. So these are the three numeric variables we have. Now we can turn these into numbers, and we'll worry about that later. For now, let's just go ahead and run this again. Data analysis, correlation, and we're just going to change this from A1 to start at D1. So we're simply going to ignore smoker region and sex for now. Hit OK. There we go. All right, so we can see that age and BMI correlated R equals about 11% here. So as people get older, and it's positive, so that means as people get older, their BMI increases. Yep, we all know that. It's sad but true fact of life. As people get older, their number of children increase, but not nearly as strong of a correlation as age with BMI. And then age and charges increase a lot more. So high correlation there. As people get older, they cost more. That's what we're really interested in here, is looking at how these other three features, and I can also do it from right here, age, BMI, and children, are related to charges. Looks like age is the biggest one, followed by BMI, followed by children. And we're going to keep this here and then run an MLR to compare the results to what we have up here in the correlation. So let's go ahead and run that now. Back to data analysis. This time scroll down to regression. Double click. Y input range, that's our label. So this is kind of a finicky tool. It's not super user friendly. Just make sure you always click here in the box first, and then click over here to charges, Control-Shift down, then click in the X range. I'm going to put my cursor somewhere over here. I'm going to hold down Control up to get back to the top, Shift over to children, Shift Control down to get all of those. All right, so we have the data. Labels are in the first row. To get to the output range, don't just click right here. Click here first on this. Then click inside. Don't forget, click inside this box or you're going to have headaches. It's going to try and overwrite your correlation. Let's come down here to I9 and go ahead and hit OK. There's a lot of other cool features that help us to interpret MLRs right here that you'll get in a stats course, which are great to learn, but we're not going to get into that depth for now. All right, summary output. So we talked a little bit about R squared before, 12%. I'm going to bold that. So this is how much of charges we can explain with the combination of age, BMI, and children. Well, this is lower than the individual correlations with age and BMI. Yeah, that's okay. That's what happens as we start to explain, the squared value turns this into R squared. So unsquared, this would be equals this raised, so the 1 divided by 2. There we go. 34% would be sort of the equivalent of taking the combined correlation of all three of those and subtracting out the portions that overlap. That makes more sense. The reason why we square it is so that the number is positive, and we interpret this as the percent. And it's not a perfect direct interpretation, but the percent of the variation in charges that is explained by the combination of all three of these variables at once. That's the definition we'll give to it. All right, so down here we have what's called an ANOVA. You might remember that from a prior chapter. Whoops. This ANOVA simply says, is the overall group of variables a statistically significant set of variables to explain charges? So you get an F score, and there's, you might remember from stats, the F and T tables that give us p-values so we can measure significance. In this case, this is 0.036 meaning it's ridiculously significant. This significance F is the same thing as p-value. I don't know why they, p-value. They should have just called it that in the first place. So the overall model has a p-value. Great, and it's really low. So that means this is a pretty good model. Altogether, we call the combination of these three variables a model. Models are ways of explaining other phenomenon. In particular, we're explaining variations in charges. Stay with me, you'll see how this works by the time we get to the end here. So now that we've got our R squared, on a side note, adjusted R squared, this is a measure that is like R squared, but it sort of discounts if these three variables are too intercorrelated. It will sort of penalize the R squared a bit. There's a very small difference between these, which tells me these aren't overly correlated, these three variables. It's not a big penalty, it's very minor. Anyway, down here is the next interesting table. So you see we've got age, BMI, and children, our individual variables. We have what's called coefficients for them. We have p-values for them. And that's all I'm going to cover for now. So I'm going to change these real quick. Actually, just all the numbers in this table. Home, numeric. Let's do let's do 3. Wow, those are really significant. All right. I didn't need to do that. I'll go back down. Okay, good enough. So a coefficient, think of this as a correlation after controlling for or removing the variance due to the other variables. Now, these don't vary between 0 and 1, not like a correlation. They're relative numbers. They're relative to each other. And we'll use them to come up with a prediction later, but think of it conceptually as this is how much age is correlated with charges after controlling for or removing the variation due to BMI in children. In other words, this is a much more accurate representation relative to these other two than this number up here. So we like these scores because they're more accurate. Now we get an associated t-stat. Before I get to the t-stat, this is standard error. This is how much error or variation we have in these scores and these estimates. Now, these estimates can't really be directly compared the way we've done it because our data are all on different scales. So age ranges from 19 to, I don't know, 70 something in this data set. BMI, it's a much tighter variation, which ranges from 15 to 35-ish. And then children has a very, very small range. So we'll come back to this a bit more, but we haven't standardized this data and put all of them on the same scale. If we had standardized it, then we could compare these directly. We could say age is definitely smaller than BMI, BMI is smaller than children. But we can't say that since the data is unstandardized. Standardizing is not necessary in all cases, and later tools that we'll use in this class will automatically standardize for us. So we're not going to worry about it for this example. Anyway, here's our error. We get an associated t-stat, which is basically a measure of the error divided by the coefficient, not exactly, but it sort of puts these two scores together in an overall comparable score. These scores here are comparable. So this tells us that age has a more significant effect, meaning more reliable. Not necessarily a larger effect, but we can count on this coefficient more often than we can count on BMI in children. Well, can we count on, or should we count on any of them at all? Well, you've heard of the rule of p less than 0.05. So p, this probability, there's an arbitrary rule that is commonly accepted that any value below a 0.05, we call that statistically significant, meaning it's good enough that we can rely on this and count on seeing a very similar coefficient to this when we collect an entirely new set of 1338 customers. So this p-value is interpreted as the probability that this score right here is wrong. And in particular, the probability that when we collect new data, that we'll get something different from these. So a very low probability means that it's very likely that we will get these scores again. These two, as you can tell, are much more likely we'll get those exact scores than this one. Now this is still below 0.05, it's still statistically significant. And what's the true difference? Well, if we were to collect another 1338 records, these would vary by a small amount, and this would vary by only a little bit more, but not so much that it bothers us. So we're interested in, at least for now, p-value and these coefficients. All right, well, how do we come up with an actual prediction? Let's do that. So it helps if you can think back to middle school, high school algebra, where you learned the formula y equals mx plus b. Or you might remember f of x equals mx plus b. So we're going to take this formula and just expand it a bit. It's the same idea. So this score right here, this is our slope. Slope is m. X is the actual value of a row. B, as you might remember, is the intercept, which we get right here. The intercept is what is the value of y when x is 0. So where does it cross the y-axis? All right, let's use an example here. Let's start with this first person, age 19, and let's plug in the actual numbers. In this case, we're going to say y equals, the m slope is 239.994 times row 2 is 19 plus, well, in this case it's a negative 6916, so I'm going to do minus 6916.243. All right, that comes out to, let's put in the actual formula here. It equals this times this plus this. There we go. So our predicted insurance charges for someone who's 19 years old is negative 235634. How is that even possible? Well, think back to in the prior chapter when we learned about the assumptions of correlation. One of the assumptions is that the data is normally, or data are normally distributed, meaning that the column, the histogram for charges has a nice bell curve. Well, is that true? Let's take a look and see what it actually looks like. So I'm going to insert chart, histogram, perfect. I'm going to actually move this, I'm going to cut it and move up to the top and take a look at it right here. Okay, clearly this is not bell-shaped. Most of our data is down here on the low end. It's positively skewed, right skewed. So this is histogram for charges. So for a correlation, both the x and the y variable, or both variables, are supposed to have a normal distribution. Let's see what age looks like. Insert histogram. I like this, puts a line through it. Not necessary. I could take the line out. Whatever. But you get the idea. This one, it's less skewed than charges is. But this histogram here for age, histogram for age, is also right skewed. Also not the way it should be. The effect of this is that when we have more data, the mean of the data set isn't going to be right here in the middle. The mean is going to be somewhere over here since there's a lot more records over here. Now, what that does is it throws off our predictions. And this is, you can learn more about this in a good stats class about the central limit theorem and normality. But the idea is when it's right skewed like this, then the value at 0, when x is 0, can actually go negative or below what the range of possible values are. So basically we'd interpret this as a 0. So this being not normally distributed means that a lot of our predictions are going to be off a little bit unless we can make an adjustment. And you might have learned in the last chapter one way to do that is to make a mathematical transformation like a natural log. We're not going to get into that right now. Or if I've got time, maybe I'll do it at the end here. For now, I just want to explain why this number is negative and know that it's not because we did anything wrong. It's just because our data are skewed. All right. Now let's take this to a more accurate prediction. So this is if we just did a simple linear regression and only had one variable, but we got two more. So what we're going to do is say that y equals m1 times x1 plus m2 times x2 plus m3 times x3 plus b. That's our formula because we have three variables and not just one. And all that means, I'm just going to You know what, I'm just going to put the formula right out here, is that we're going to include those other coefficients right here for BMI in children, as well as the actual values of BMI in children. So let's put in the formula. This is going to equal age coefficient times 19 plus, oh, I always do that. Sorry. If you hold down shift too long as you're moving around, it does that. Plus the BMI coefficient, oh, and I better do a parenthesis, plus the BMI coefficient times, there I go and do it again, times that same person, so it's all got to be data for the same record. So I'm trying to predict this particular customer's insurance charges. I want to grab all the actual values for that customer. Okay, I gotta stop typing so fast. Finally, times the coefficient for children, or plus the coefficient of children times the actual value of children. Finally, plus B plus, seriously, the intercept, which is right here. All right, this is a little better. It's a little closer, or at least in a valid range. For this particular customer, because they're still on the lower end, below the mean of charges, our predictions are still a little low. And so you can see their actual value for this customer of charges is this, and what we predicted was that. So what I want to do is let's come up with this prediction for every record and see how off we are on average. So I'm going to insert a row right here. I'm going to call this predicted value, and then I'm going to add another column. Call this one difference, and then actually one more. I'm going to make one for absolute difference. And then one more, sorry, I keep forgetting about more. Then squared difference. Because we're going to come up with two different measures of accuracy, of how good this model is that we've built. And again, by model, I mean this set of coefficients with this intercept, which and the fit of this model is indicated by this overall R squared. However, we've got a couple other ways to measure fit. This is just one of several good ways. Let's start by coming up with our prediction. To do this, I'm actually going to insert a row up here, and I'm going to copy and paste these values above these coefficients. So I'm going to paste transpose. Oh, whoops, I didn't do transpose like I meant to. Paste transpose, there we go. I'm going to get rid of these borders because I'm a little OCD. All right, so I'm going to put our coefficients there. Predicted value then, this is going to equal, I like the sum product function in Excel. So I'm going to say this array, comma, this array, close that function out, add to that function the intercept. So what sum product does is essentially exactly what we did in our formula down here. It says take this value times that value plus this one times that one plus this one times that one. The only thing we need to do is we need to make sure that this array stays put while this array automatically changes as this formula is copied down the list of data. So I'm going to highlight D1 to F1, and I'm going to hit F4. Whoops, forgot my function keys on. F4, there we go. And so that puts those dollar signs, which means keep those rigid. And I also want to do the same thing here on N26. Technically, I don't need to keep the column in one spot because I'm only copying down, but it's all right. Okay, I'm going to select this, hover over the bottom right corner till your outlined cross turns into a filled-in cross, or plus sign, whatever you want to call it. Double click, and it pastes your formula all the way down. So you can take a look through these and see some are definitely more accurate than others. Well, that's all right. We've only got 3 variables, and we haven't even used these other ones yet, so we'll come back to this later and improve it. For now, what I want to do is now calculate the difference. This equals the predicted value minus the actual value. Let's copy that one down. So this is how off we are on each prediction. Now we want an overall measure of how good our prediction is, which R squared is one way to indicate that, but we're going to come up with two more. And we'll do that by using, first of all, taking the absolute value of the difference and also the difference squared equals difference times difference. Oh, what did I do wrong here? Oh, I missed the first parenthesis. Oh, they got it for me. Okay. Copy these down. All right. Two values here. I'm going to insert another row so you can learn their names. I'm going to call this one mean absolute error and mean squared error. Or we're going to come up with the root mean squared error. So mean absolute error is pretty straightforward. It's nothing more than the average of how off we are on every one of our predictions. So there it is. We're off by 9,000 on average on all of our predictions. Well, given that insurance ranges from like 1,000 up to, I think some of them were like 60,000. What were these over here? 46,000 to 87,000, up to 87,000. So given that wide range, that's an $80,000 range. Being off by 9,000 isn't too bad. However, most of our data is not up here in these high ranges. Most of it's down here. So it's kind of not a really good indicator of just how good or bad our model is, because this is averaging out everything, and our data are not normally distributed, which means our predictions are a little bit off, as you remember right here. So we don't trust MAE as much when the data are not normally distributed. When we have this problem, we prefer to use root mean squared error. And it gives us a bit of a better idea of just how good or bad our model is. So this one, all we do is we take the squared value, we take the mean of that, first of all, the average of that square value, and then the square root of that average. So I'm going to go average, get all those values. Oops, I actually started with the column header. There we go. Got that. And then I'm going to raise it to 1 divided by 2 to get the square root. There we go. 11,355. This is a more accurate representation of just how good or bad, whatever you want to call it, our model is given our data over here. So I've given you 3 metrics now that we can use to evaluate what we call model fit. Mean absolute error, root mean squared error, and then R squared. We like all 3 of those. So this is a good primer on multiple linear regression. In follow-up videos, we're going to learn how to handle these categorical variables over here, and then also turn these results into a prediction calculator.